Okay, ladies and gentlemen, welcome to the third and final video for our graphing rational functions notes, Chapter 2, Section 5 of your McGraw-Hill Pre-Calculus book. This video is going to cover the details, the special cases that could come up about graphing rational functions. The second video in this series showed the basic idea of how to graph a rational function. This third video is going to talk about situations that can come up that would make it more difficult, as it were. So the first thing we need to talk about here is oblique asymptotes. This would be case 3 when we're checking for a horizontal asymptote. If the numerator's degree is greater than the denominator's degree, that means there is no horizontal asymptote because there's an oblique asymptote, or potentially a quadratic asymptote or a cubic asymptote. But we're only going to deal with oblique asymptotes at this level. When we look at case 3, what we're saying is the degree of the numerator is going to be greater than the degree of the denominator. And once we make sure that nothing cancels, which would be an example of a whole, which we'll talk about here in a minute as well, then we will use long division to find the equation of that oblique asymptote. So again, it's a three-step process. To find the oblique asymptote, we make sure that we've canceled any factors from top to bottom that exist that are common. Anything that's common from top to bottom can be canceled because that would indicate that a whole. And then we'll carry out long division on whatever is left in that situation. We don't care at all about the remainder from that long division. We only care about the quotient, because the quotient, the answer after we divide, is the equation of the oblique asymptote, and it will be in the form y equals mx plus b. So let's look at some examples of this. Again, it says find all the asymptotes for the following functions. We're going to add to those directions. We're also going to be spotting any holes that might pop up, and I don't remember how many there are, but we're just going to look at the whole process of finding horizontal and vertical asymptotes, oblique asymptotes, and holes would be our special cases that could come up in this situation. So to do this, the big thing is the first thing we do is the horizontal asymptote, which for the horizontal asymptote we look at the degree of the numerator and the degree of the denominator. In this case, the degree of the numerator is 2, the degree of the denominator is 1. Since n is greater than d, that tells us we have an oblique. So we do a quick check to make sure that nothing factors or nothing cancels. So we just quickly factor out the numerator and the denominator if possible. Nothing cancels. Okay, so we don't have that possibility. So then what we do is we carry out long division. We are dividing x squared plus 2x minus 3 by x minus 2. We're basically doing the division problem that is listed in the problem. So again, that process is one that we've already gone over in this school year. We need to ask ourselves, what do I need to multiply x by to get x squared? The answer is x. X times x is x squared. X times 2 is negative 2x. Draw the line, change both signs, add down. Bring down the negative 3 and do it again. What do I need to do to x to turn it into 4x? Well, I need to multiply by 4. 4 times x is 4x. 4 times negative 2 is negative 8. Draw the line, change both signs, add down. We do not care about the remainder at all. What we care about is the quotient, because the quotient is the equation of our oblique asymptote. The oblique asymptote is the line y equals x plus 4. Going back to vertical asymptotes, we're looking for division by 0. Help if I could spell. In the original problem that doesn't cancel. Well, that would be when x minus 2 equals 0, so we would have a vertical asymptote of x equals 2. And that would be every single asymptote for that example. On letter B, the numerator is 2. The denominator's degree is 2. Since the numerator is equal to the denominator, we have a horizontal asymptote in the form y equals a over b, where a is the lead coefficient in the numerator, and b is the lead coefficient in the denominator. Both are 1. So our horizontal asymptote is the line y equals 1. For vertical asymptotes, we need to consider the factored form. The numerator of our original function factors into x plus 3 and x plus 1, and the denominator factors into x plus 1 and x minus 1. Now this is important because you should immediately notice that the x plus 1's should cancel. They should cancel out in this situation. Okay, so we're basically going to go in there and we're going to be canceling those two values, which what that indicates is that since x plus 1 cancels, this function has a hole. At x equals negative 1. Not an asymptote, it has a hole. Okay, it does, however, have a vertical asymptote when x is equal to positive 1, because that would cause division by 0. So the negative 1 is not an asymptote because that factor cancels from the numerator to the denominator. The x minus 1 does not cancel, so x minus 1 would generate a vertical asymptote of positive 1. Okay, on the last example, the numerator is 3, the denominator's degree is 2. So n is 3, d is 2. Since n is greater than d, we have an oblique. We do need to check and make sure that nothing cancels, so we do need to take a quick look at the factored form, and I will write that down here because we're going to have to look at it for the vertical asymptotes anyway. The top factors by grouping to give us a factor of x squared plus 3 and a factor of x minus 2. And the denominator gives us factors of x minus 2 and x minus 4. So again, the x minus 2's will cancel, which means we have a hole at x equals 2. And we have a vertical asymptote at x equals 4. Now the reason why we check that first is because that makes the long division somewhat easier, because we can divide the reduced form of x minus 4 dividing into x squared plus 3. Remember that we do have to put in a 0 for the x term so that long division will work. X times x could give us x squared. X times x is x squared. X times negative 4 is negative 4x. Draw a line, change both signs, add down. Bring down to 3. Means we have a 4 there. 4x minus 16, but we really don't care because the remainder doesn't matter. Okay? What matters in this case is the x plus 4, because it means our oblique asymptote is the line y equals x plus 4. So that would be all of the asymptotes that exist for that equation. Okay. So, again, this becomes a 6-step process eventually for any rational expression, no matter how complicated. We factor the numerator and the denominator. The reason we do that is to look for vertical asymptotes and holes, both of which are found based on the factors of the denominator. If a factor from the denominator cancels, that indicates a hole. If it does not cancel, it indicates a vertical asymptote. We then look at the degree of the numerator and the degree of the denominator and compare them to decide whether we have a horizontal asymptote or an oblique asymptote. We cannot have both. We will have one or the other. Then we will draw all of those asymptotes on the graph, make a table for the points between those vertical asymptotes. Remember the middle sections need at least 3 points and the outer sections need at least 2 points. Then we sketch that graph and go back to add any holes in as needed. So here is a function. We're going to go through that entire process here. Start off with vertical asymptotes. Well, the first thing we need to do is factor that numerator if possible, and it does factor. We've got that trinomial of 2x squared minus 5x minus 12. We should remember our advanced factoring, which says we're looking for numbers that multiply to negative 24 and add to negative 5. Well, that would be negative 8, positive 3, which means I'm going to be breaking that middle term up into a negative 8x and a positive 3x based on these numbers, which would then give me factor by grouping. I can take a 2x out of the first one, leaving me with x minus 4, and a 3 out of the second one, leaving me with x minus 4, which means that factors into x minus 4 and 2x plus 3. So the factored form of our function would be x minus 4 times 2x plus 3 over x minus 2. The big thing here is that the x minus 2 does not cancel, which means we have a vertical asymptote at x equals 2, and we do not have any holes, which means we don't need to worry about that section. There are no holes. Then we look at the horizontal or oblique asymptote. For that, we look at the degree of the numerator and the degree of the denominator. The degree of the numerator is 2, the degree of the denominator is 1. Since n is greater than d, we have an oblique asymptote. And we need to divide. So we are going to carry out long division to find the equation of the oblique asymptote. X minus 2 is dividing the numerator 2x squared minus 5x minus 12. X times 2x would give us our 2x squared. 2x times negative 2 is negative 4x. Draw the line, change both signs, add down. Would give us negative 1x minus 12. To turn x into negative 1x, I need to multiply it by negative 1. Negative 1 times x is negative 1x. Negative 1 times 2 is 2. Draw the line, change both signs, add down. Now we still do not care about this. What we care about is this right here. The oblique asymptote has an equation of y equals 2x minus 1. So the next step in the process is to graph all of those asymptotes on our graph. We have a vertical asymptote of x equals 2. And we have a horizontal asymptote of y equals 2x minus 1. Now remember, we start that at negative 1. We go up to right 1. Or down 2 and left 1. So those would be our asymptotes. We have x equals 2, which is the vertical asymptote, and y equals 2x minus 1, which is the horizontal or the oblique asymptote. Now, we then need to make a table of values. This is only 2 sections, so hopefully we'll be able to get this done with just 4 numbers. 2 numbers from the left of x equals 2, I'd use 1 and 0. And 2 numbers from the right of x equals 2, hopefully 3 and 4 will work out rather nicely. So when we plug those numbers into the original equation, we can use either the original equation or the factor form. It doesn't matter which one we use, but we're evaluating y when x equals 1. That would be 2 times 1, which is 2, minus 5 times 1, which would be negative 3, minus 12 would be negative 15, over, on the bottom, 1 minus 2 is negative 1, so that's 15. Not going to be real helpful to us. That does mean we're probably going to have a problem here, and we're going to have to add some points to our table to make it work. Now, when we do 0, 0 works out okay, because that's 0 minus 12, which would be negative 12, over 0 minus 2, which is negative 2. That is positive 6, and that is a value that we can actually graph on our graph. So we do need to add a point. Let's do negative 1. That should give us the shape that we need to establish what this looks like. So when we do -1, we have 2 times -1 squared, which would be 2, plus 5 would be 7, minus 12 would be -5. And in the denominator, -1 minus 2 would be -3. So we'd be looking at a value of 5/3. 5/3, of course, being 1 2/3, meaning we would be around right there. Now, it might be worthwhile to do one more point just to make sure we have the shape established correctly. So if we do -2 real quickly, that would be 8 plus 10 minus 12 on top. So that would be 6. And on the bottom, we would have -4, which means -3/2 would be that value. That would be right here. So hopefully that's enough for us to establish that that curve is going to be hugging that asymptote eventually. It's then going to come pass through those points, and it's going to exit along the oblique asymptote. Now the other section, we're going to start with 3, and I anticipate that 3 is not going to help us out much, so we're probably going to need to add some points. We plug 3 in. 2 times 3 squared would be 18, minus 5 times 3, which is 15. So 18 minus 15 is 3. Minus 12 would be -9 over 3 minus 2, which is 1. So that's -9. That is not on the graph. That is not going to be helpful. Plug in 4. 2 times 4 squared would be 32. Minus 5 times 4 would be 12. Minus 12 would be 0. So 4, 0 is a point that we can graph. That's a helpful point. But we do need at least one more point. So I'm going to extend my table a little bit more, and I'm going to plug in 5. 2 times 5 squared would be 50. Minus 5 times 5 would be 50 minus 25, which is 25. Minus 12 would be 13 on top. On the bottom, 5 minus 2 is 3. So 13/3, well, that would be 4 1/3. So when we're plotting that, 5, 4 1/3, 2, 3, 4, and just above that. So again, we know it's going to come in along that vertical asymptote. It's going to pass through these points, and it's going to exit along the oblique asymptote. That's what that graph is going to look like. All right, let's do another one. This is the last slide of the notes. So once again, we need to have the factored form. So the top of this will factor into x minus 3 and x plus 2. The bottom has an x for a greatest common factor. And then what's left would be x squared plus x minus 12, which would be x plus 4 and x minus 3. Which means that if we look at this, the x minus 3's would cancel, which means that we do have a hole at x equals 3. Okay, we have a hole when x is equal to 3. Because x minus 3 canceled, so when x equals 3, that's still not allowed to be part of the original equation, but it is a hole. Okay, we also have we have 2 vertical asymptotes. We have one at x equals 0 and one at x equals -4. Then we go to the horizontal or oblique asymptote. The degree of the numerator is 2. The degree of the denominator is 3. Because n is less than d, our horizontal asymptote is the line y equals 0. So we graph those asymptotes. We have a horizontal asymptote of the axis. The x-axis is an asymptote. Thing didn't exactly do what I wanted it to do there, but that's okay. We'll get that fixed, no problem. We have 2 vertical asymptotes, one at 0 and one at -4. Now, one important note here is that we have what is called a reduced form of this function. which we can actually just graph that. We can use that equation to generate our table. So when we look at our graph, we have 3 sections. So from the left section, we're going to do -5 and -6. From the middle section, we're going to do -3, -2, and -1. And then from the right section, we are going to do 1 and 2. And we're also going to locate the whole by plugging in that value x equals 3 to the reduced form. So for the left end, we plug in -5 to the reduced form. -5 plus 2 is -3 on top. And -5 squared plus 4 times -5 would be 5 on the bottom, or -3/5. When I plug in 6, I have -4 on top. And on the bottom, I have 36 minus 24, which is 12. That would be -1/3. So -5, -3/5 would be a little over halfway from 0 to -1. And -6, -1/3 would be significantly closer to the axis, indicating that that section of the graph is hugging the asymptote and then exiting on the bottom. In the middle section, -3 gets plugged into the reduced form, would give us -1 on top, and 9 minus 12 would be -3 on the bottom, so it's +1/3. -2 goes in, that is 0 on top, which means the whole thing is 0. And -1 goes in, giving us -1 plus 2, which is 1 on top, and 1 minus 4, or -3 on the bottom, which is -1/3. Well, that's interesting. That section actually crosses the axis. So let's graph those points so we can look at it. -3, we are at +1/3. -2, we are on our horizontal asymptote. -1, we are at -1/3. Now these middle sections, what happens here is it actually has, when we graph this thing, it's coming in along the asymptote. It is passing through those 3 points and then exiting along the asymptote on the bottom. So that section actually does cross the horizontal asymptote. And that can happen in middle sections, so don't be surprised if it happens on your assignment. Finally, for the right-hand section, we plug 1 into the reduced form and we get 3/5, 3/5. We plug 2 in and we get 4 on top. And on the bottom, we get 4 plus 8, which is 12. So that would be 1/3. So we have 3/5, 1/3 is just over half. And then 2 is at 1/3. And then we do need to plug in 3, which would be a 5 on top. And 9 plus 12, which is 21 on the bottom. Because what that means is that we have a hole in the graph right there at 3 5/21. So when the graph comes in and passes through these points, there's actually going to be a hole at x equals 3 that we have to indicate in our graph, and then it will continue on along the axis. So that is how we handle asymptotes, oblique asymptotes and holes when it comes to the equations and the graphing. Hopefully this has been helpful. Thank you for your time and attention.